So hello everyone, welcome back to NPTEL lecture series on cycloaddition reactions. So in the last 9 lectures, we talked extensively about 4+2 cycloaddition reaction. We talked about normal 4+2 cycloaddition, inverse electron demand 4+2 cycloaddition reaction, hetero-Diels-Hall reaction, intramolecular Diels-Hall reaction type 1, type 2, Alder-Rickert retro-Diels-Hall reaction, dehydro-Diels-Hall reaction, and we also talked about the use of Lewis acid as well as asymmetric Diels-Hall reaction. So what we'll do today and in the next few lectures, we will move to 1,3-dipolar cycloaddition reaction or 3+2 cycloaddition reaction. In the case of 4+2 cycloaddition reaction or Diels-Hall reaction, the reaction is between a diene and dienophile. Whereas in this case where we use a 1,3-dipole, okay. 1,3-dipole means this 1,3-dipole where you have 4 pi electrons across 3 atoms. Since we are using the term dipole, the 2 pi component, which is alkene, is called dipolarophile. Okay. So in the case of 1,3-dipolar cycloaddition reaction, what we do, we react 1,3-dipole with a dipolarophile. Okay. Since this is a 3+2, so in the end what you get is a 5-membered ring. In the case of 4+2, in the case of Diels-Hall reaction, you get a 6-membered ring, whereas in the case of 1,3-dipolar cycloaddition, you get a 5-membered ring. Okay. And here again there are 2 types of outcome. One, if you have a dipole like this where you have only one double bond in the dipole, that will give a 5-membered ring like this. However, if the dipole has a triple bond, not a double bond, then in the 5-membered ring you will get a double bond. Okay. In the first case you don't get a double bond. In the second case you get one double bond. And there is also one more where the dipolarophile, if you have a triple bond, then you will get one more double bond. Okay. So the third possibility, you get 2 double bonds. Okay. And as I mentioned, this is a reaction between a dipole having 4 pi electrons and dipolarophile having 2 pi electrons. If you look at the history of 1,3-dipolar cycloaddition reaction, the very first dipolar cycloaddition reaction was reported by Buchner in 1888. Actually, this reaction was between a diazoacetic ester and dimethyl fumarate to form 1-pyrozolene. So this was a reaction almost, you can see, close to 140 years ago this reaction was reported, even before Diels-Hall reaction was reported. The second 1,3-dipolar reaction which was reported was based on nitrones. That was in 1898. Beckmann actually discovered nitrone. So nitrone is nothing but N oxide of imine. So this is imine, and if it is N oxide of imine, then it is called nitrone. So this was discovered in 1898, and 5 years later Werner reported the use of nitrile oxide. Nitrile, in organic chemistry, organic cyanides are called nitriles, and N oxide of nitrile is also a type. And afterwards, after 25 years only, Diels-Hall reported the use of diene and dienophile in 4+2 cycloaddition reaction. In late 50s, Rolf Eusgen, he reported a 1,3-dipolar cycloaddition reaction between azides and alkynes to form a triazole. Okay, this we normally call it as Hughes-Gunn cycloaddition. In fact, this became very popular after Sharpless made it as a click chemistry, okay, with the copper catalyst. So, copper catalyzed 1,3-dipolar cycloaddition between azides and alkynes became very famous because it has been renamed as click chemistry. Okay, we will discuss, maybe we will talk about click chemistry in one of the lectures. So, like dienes, when we talk about dipoles, okay, dipoles can be broadly classified into two types. One is allyl anion type, other one is allynyl or propargyl type. Okay. So, what is allyl anion? So, if you look at this structure, this looks like allyl anion. Okay. You have 2 pi electrons and then you have anion. So, that means you have 4 electrons distributed between these 3 atoms. And if you look at the structure, this allyl anion type dipoles are always bent in nature. Okay. So, this can be drawn either in the octet structure form or sextet structure form. Okay. This is one class of dipole. The second one is the propargyl type or allynyl type dipole. Okay. So, this is propargyl, you can see here a triple bond, and here you have positive charge and here you have negative charge. So, this is propargyl anion type, and one can also write another canonical structure. So, here you see it looks like allynyl. Okay. So, these are two different types of dipoles. This you should remember, allyl anion type, the other one is allynyl or propargyl anion type. Okay. Now, let us see some examples of allyl anion dipoles. So, again there are few subdivisions. What we do, we start with having nitrogen in the middle. There are 3 atoms. So, first let us keep nitrogen in the middle. The simplest one, which is commercially available, well known, is nitro group. Okay, you can see nitro group. So, here it is a classical dipole. Now, what you do next, you replace this oxygen with carbon. So, this is called nitrones. I already mentioned nitrones is nothing but N oxide of imine. Okay. So, that is nitrone. Now, replace oxygen with nitrogen. This is called azomethane imines. Okay. Azomethane imines. Then you replace nitrogen with carbon. So, this is called azomethane ylide. You know ylide, ylide means it should have the carbon should have negative charge and then adjacent heteroatom should have positive charge. Okay. Normally we talk about phosphorus ylides, which are used extensively in Wittig reaction. Here it is nitrogen ylide, and the nitrogen is part of azomethane. That is why this is called azomethane ylide. Then instead of carbon, you can have oxygen. So, that is called azoxy compound. So, this allyl anion type dipole has all these dipoles, nitrogen is in the middle. Okay. Now, let us see whether you can replace nitrogen with other atoms. For example, instead of nitrogen, if you have oxygen in the middle, the simplest dipole which we all know is ozone. Okay. Then you replace this oxygen with carbon, then this is called carbonyl oxide. You have carbonyl and then you have oxygen. So, it is called carbonyl oxides. Now, you replace the oxygen here with carbon, then this is called carbonyl ylides. Again, you can see ylide means you have negative charge on the carbon and then adjacent heteroatom as a positive charge. So, this is part of carbonyl group. So, that is why this is called carbonyl ylides. And if you replace the carbon with nitrogen, then this is called carbonyl imines. And instead of carbon, if you have nitrogen on the left hand side, this is called nitroso-imines, and if you have oxygen in place of nitrogen, this is called nitrous oxide. Okay. So, now let us move to the propargyl or allynyl anion type dipoles. Again here there are two types. One is based on diazonium. Okay. So, we call it as diazonium butane intermediates. So, here the central atom is nitrogen. Okay. The central atom, you can see it is nitrogen, this is nitrogen, this is nitrogen. And more importantly, if you look at this, the whole thing is N triple bond N. Okay. And the only other atom you can change. If it is nitrogen, this is called azide. If it is oxygen, it is called nitrous oxide. If it is carbon, this is called diazo alkanes. Okay. You keep nitrogen and then attach with nitrogen, oxygen and carbon. So, there are three types of propargyl type dipoles. Then the second type is nitrillium. Here instead of both atoms nitrogen, one is nitrogen, other one is carbon. Okay. So, this is nothing but nitrile and oxide, nitrile oxide. Here the oxygen is replaced by carbon. So, it is nitrile ylides and the carbon is replaced by nitrogen. So, it is nitrile imine. Okay. So, these are 6 different propargyl type dipoles known in the literature. Now, like 4+2 cycloaddition reaction. So, 1,3-dipolar cycloaddition can be further classified. So, there are 3 types of 1,3-dipolar cycloaddition. Type 1, in this case, like normal 4+2 cycloaddition reaction, the HOMO of the dipole interacts with LUMO of the dipolarifier. In the case of type 2, here the energy level of HOMO of the dipole and the energy level of LUMO of the dipolarifier are in the same level. Okay. So, then both interactions are possible, HOMO with HOMO of dipole with dipolarifier and vice versa. Type 3, here the LUMO of the dipole interacts with HOMO of dipolarifier. Okay. So, these are 3 types. Again I will explain about type 3. In the case of type 3 dipolar cycloaddition, the energy level of dipole and dipolarifier are almost same. Okay. So, then a HOMO and LUMO of both dipole and dipolarifier can interact. Okay. Let us discuss the energy diagram itself. So, in the first case, the type 1, you can see here, this is the dipole, this is the dipolarifier. Here the HOMO of the dipole interacts with LUMO of dipolarifier. In type 2, you can see here the HOMO of dipole and dipolarifier and LUMO of dipole and dipolarifier are at the same level. So, both interactions are possible, either this or this, both interactions are possible. In type 3, the HOMO of dipolarifier interacts with LUMO of dipole, exactly opposite to type 1. So, it is like one is like normal Diels-Alder reaction, other one is like abnormal Diels-Alder reaction. This we have discussed. Okay. So, type 1 is like normal, type 3 is like abnormal and type 2 is in between. Okay. And which dipoles will undergo type 1, which dipoles will undergo type 2 and type 3 and so on. Azomethane ylides, azomethane imines are known to undergo type 1. Nitrones, nitrile oxides, they undergo type 2. Ozone and nitrous oxides follow type 3. So, this is when you mix these two and then do the 1,3-dipolar cycloaddition reaction by heating. However, when you use a Lewis acid, the whole scenario may change. So then anyone can follow type 1, anyone can follow type 2 and so on. There will be significant change if external reagents are added. Okay. So let us start with a very simple and well known dipolarifier before we go to nitrones, carbonyl halides and nitrile oxides and so on. Okay. So ozone is a well known dipole, and here all the atoms are oxygen, and it is also belonging to allyl anion type. It is a bent dipole. So what is the use of ozone? We all know if you have a double bond, if you treat with ozone followed by treatment with dimethyl sulfide, triphenyl phosphine, so on, it will cleave the double bond to two carbonyl groups. So how does it happen? One, it undergoes the first step is the 1,3-dipolar cycloaddition or 3+2 cycloaddition reaction. So that will give you the mal ozonide. So this is the first intermediate you get. Now this undergoes a retro 3+2. This lone pair on the oxygen comes and then opens, and then you get one side carbonyl, other side another dipole. Okay. Now keep this as such, but rotate this 180 degree. Okay. Rotate like this. When you do that, you have the dipole written this way. This can undergo now another 3+2 cycloaddition reaction. If that happens, you get the ozonide. So this is the ozonide. Now ozonide, again it's unstable, so you have to cleave the ozonide. So what you do, you can treat with dimethyl sulfide, which has a lone pair, and this dimethyl sulfide will attack one of the oxygen of the peroxide and breaks the oxygen-oxygen bond, and in the process what you get is 2 aldehyde, and dimethyl sulfide becomes dimethyl sulfoxide. The dimethyl sulfide takes the extra oxygen and becomes dimethyl sulfoxide. Okay? So instead of dimethyl sulfide, one can use triphenyl phosphine, one can also use zinc. So in the case of triphenyl phosphine, it will become triphenyl phosphine oxide. If you use zinc, it will become zinc oxide. You can also cleave the ozonide with sodium borohydride. So this is called reductive workup. You will directly get the corresponding alcohol. One can also do oxidative workup, where you can use peroxide, for example hydrogen peroxide and acetic acid. You can oxidize this malozonide directly to corresponding carboxylic acid. So either you can get carbonyl group or alcohol or carboxylic acid, depending on the nature of workup. Okay? And when it comes to reactivity, the more substituted double bonds will react faster than the less substituted double bond, or electron rich double bonds will undergo reaction faster than the electron deficient double bonds. Particularly if you take this example, this is a tri-substituted alkene, this is also a tri-substituted alkene, but this double bond will undergo ozonolysis faster than the left hand side alkene, though both are tri-substituted, because this is more electron rich. And one can also use sodium sulfate. Okay, the sodium sulfate will take the extra oxygen and become sodium sulfate to get aldehyde. So dimethyl sulfide, zinc, triphenyl phosphine and sodium sulfate will give corresponding carbonyl group. Okay. And as I said, you can do oxidative workup. For example, if you cleave this double bond with hydrogen peroxide, you should get corresponding dicarboxylic acid. And if you have alpha beta unsaturated ketone, if you do ozonolysis followed by oxidative workup, you get a ketocarboxylic acid, where if this double bond is cleaved, you get a carbonyl group on the right hand side, and the left hand side you lose one carbon and you get carboxylic acid. So, before I proceed to other dipoles, I will talk about one name rearrangement which is part of this ozonolysis called Craigie rearrangement. So, this was discovered in 1944 by Craigie and is also a small class of Baeyer-Williger oxidation. So, this rearrangement is nothing but rearrangement of peroxyester. This peroxyester undergoes rearrangement to give 3 different compounds to ketone, ester or carbonate and alcohol. So, for example, if you take an alcohol and then treat with this peracid, it forms the peroxyester. This peroxyester then undergoes rearrangement to give, this becomes ketone, this becomes carboxylic acid and this becomes alcohol. How does it happen? Okay, let us see. So, when you take this peroxyester, then if you treat with any acid, so this carboxylic acid will go out because it is a good leaving group, and while doing that the better migrating group among R1, R2, R3, that will migrate to the other oxygen. So, that is how you generate a carbocation here. Now, the water will attack to give this intermediate and this will open up to give a ketone and alcohol. So, basically what you get is a ketone, carboxylic acid and alcohol. Let us take one specific example and then discuss. So, this is called carbon epoxide. The carbon is a well known monoterpene and then epoxidation of the electron deficient double bond. Now, you have the disubstituted alkene which upon ozonolysis followed by treatment with acetic anhydride and triethylamine, you get this intermediate. And this upon further treatment with methanol, you can see this isopropenyl group is converted into OH via Craigie rearrangement. How does it happen? First, when you treat with ozone through series of 3+2, retro 3+2, 3+2, it forms the ozonide. Now, the ozonide undergoes opening to form formaldehyde and dipole. The left hand side goes as formaldehyde, the right hand side is a dipole. You are doing this reaction in methanol and acetic anhydride. So, what will happen? Methanol will add to this carbon and O minus will be attacking the acetic anhydride. So, you get this intermediate. So, this is the same intermediate. Now, if you take this intermediate, then addition of methanol, now the lone pair on the oxygen, you can see here lone pair on the oxygen, make sure that this bond migrates to the other adjacent oxygen so that the acetate comes out. Okay, that will give you this intermediate. Now, if you look at this intermediate, again addition of methanol, okay, methanol will add here. You will get methyl acetate and corresponding hydroxyl group. Okay. So, overall if you look at Craigie rearrangement, the key reaction is dipolar cycloaddition between the double bond and ozone to give this ozonide, and again it undergoes a retro 3+2 to form this dipole and release formaldehyde, and this intermediate undergoes another nucleophilic addition of methanol followed by quenching with acetic anhydride, and further rearrangement gives this hydroxyl and methyl ester. And in the process what we have done is converting this into OH. So, this is a very interesting sequence of reaction where the double bond is completely cleaved and also the carbon is completely removed. Okay. So, I will stop here for today, and the next few lectures we will talk more about more dipoles in 1,3 dipolar cycloaddition reaction. Okay. So, thank you.